Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 and we will be presenting about stationary points and partial differentiation. But before we start, let me introduce my group members. My group members are Muhammad Hasrul Hanif bin Muhammad Hazir 1212964, Muhammad Zikri bin Yaziz 1212434, Tuan Nurain Fatiha binti Tuan Abdul Rahman 1212966, Khalida Khairina binti Muhammad Khairul Anwar 1212965, and myself Nur Aini Rashika binti Sairin 1212940. So, we will be covering Chapter 4 from stationary point, classifying stationary points until partial differentiation and question related to the topic. So, let's get started.
We start with stationary points. Stationary points is a point where the derivative of the function is equal to 0. There are three types of stationary points. First, local maximum, local minimum, and lastly, point of inflection. Firstly, local maximum. You can see that when we pass through a maximum, the gradient goes from being positive to being negative. For local minimum, we can see that when we pass through a minimum, the gradient goes from being negative to being positive. Meanwhile, for point of inflection, when we pass through the point of inflection, we should note that the gradient remains of the same sign. So either positive on both sides or negative for both sides.
Next, I will explain about classifying stationary points. To classify the stationary points, we need to use second derivative where we have to differentiate a function twice, so we can get d squared y over dx squared or f prime prime x. We know that stationary points have local maximum, minimum, and point of inflection, so we use first test and second test to classify them. Basically, first test is used to decide whether a stationary point is at a maximum or minimum. If d squared y over dx squared is bigger than 0, so we have a minimum point, which means graph is at positive area and the stationary point is concave up. But if d squared y over dx squared is smaller than 0, so we have a maximum point, which means graph is at negative area and the stationary point is concave down. Meanwhile, second test is used when d squared y over dx squared is equal to 0. Find two values just to the left and right of the stationary point, then calculate f prime x for each. If f prime x to the left is lesser than 0 and f prime x to the right is bigger than 0, we have a minimum point. If f prime x to the left is bigger than 0 and f prime x to the right is lesser than 0, then we have a maximum point. But when f prime x to the left and right have the same sign, so we have a point of inflection.
Okay, next we will learn about partial differentiation. So we use partial derivatives to differentiate function with the multiple variables. By differentiating with respect to one variable, treating all other variables as constant, we can use the notation y equal to f in bracket xz to mean that y is a function of x and z, where x and z are independent variables. For example, here we have an equation y equal to x squared plus zx, which is we have more than one variables, which is z and x. So for y equal to f in bracket xz, the partial derivative of y with respect to x is denoted as dy over dxz, which is z is outside the bracket. So we must take note that some books just use the notation dy over dx, taking it as understood that all other variables except x are taken as constant. Alright, we move on to the next slide. This is the solution for the equation that we have seen in the previous slide. y equal to x squared plus zx, find dy over dxz. Solution. We can treat z as a constant and differentiate the equation with respect to x. So the equation y equal to x squared plus zx, then we must differentiate each term. Dy over dxz equal to d over dx bracket x squared plus z plus d over dx bracket zx. So after we differentiate, we will get 2x plus z for the final answer. Okay, we try to answer these questions that related with the topic partial differentiation. Y equal to 2 ln z plus z plus sin zx, find dy over dxz. To answer this, we must notice that z outside the bracket is a constant, and we must differentiate this equation with respect to x. So y equal to ln z plus sin zx, then we must differentiate each term. Dy over dxz equal to d over dx 2 ln z plus d over dx 1 sin zx. For the first term, you must use the formula d over dx. Ln b equal to 0 as ln b is a constant. And the second term, we must use the formula if y equal to a sin bx, then dy over dx equal to a times b times cos bx. So we will get 2 times 0 plus 1z, 1 times z times cos zx, then 0 plus z cos zx, and lastly the final answer for this question is z cos zx.
The question asks to find the coordinate of the stationary point. The equation given is y equal to x power of 2 minus 4x plus 1. The first step we need to do is differentiate the equation. After we finish differentiate it, we equal the equation with 0, and we can find the x value, and the value of x will be 2. Step 3 is we need to put the value of x, which is 2, into the first equation to find y. And we will get y equal to negative 3, so the coordinate of the stationary point is 2 and negative 3. So now let's move on to the next question. The curve C has a equation y equal to 3x power of 4 minus 8x power of 3 minus 3. The question asks to find the dy dx. So we need to differentiate the 3x power of 4 minus 8x power of 3 minus 3, and we will get 12x power of 3 minus 24x power of 2. The next question is we need to find the second derivative. So we need to differentiate again the equation, and we will get 36 power of 2 minus 48x. The next question is verify that C has a stationary point when x equal to 2. So we need to substitute x equal to 2 into the dy dx equation. Then we will get the answer 0. Therefore, the stationary point of the curve is at x equal to 2.
For the next question, we need to find dy dxz and dy dzx from the equation of y equal to x to the power of 2 plus zx. For dy dxz, the z we will make it as a constant. So when we differentiate the equation of y equal to x to the power of 2 plus zx, we will get 2x plus z. Next, for dy dzx, we will make x as the constant. So when we differentiate the x x to the power of 2, we will get 0, because when we differentiate the constants, we will get 0. Next, when we differentiate the zx, we will get z. So the derivative of dy dz, we will get z. The next question, the ideal gas equation is PV equal to nRT. Find dV dTp and dt dPV. For the first question, we can find dV dTp by first making V as the subject in the equation. This is done by dividing both sides with P and produce V equal to nRT over P. And then we can differentiate with respect to T, and we make T as the constants. So we will get dV dTp equal to nR over P. For the second question, we do the same process to find dt dPV. First, we make T as the subject by dividing both sides with nR, and we get T equal to PV over nR. Before we differentiate the equation, we need to make V as the constants. So after we differentiate the equation, dt dPV is equal to V over nR.